So, recording already. So, yesterday we went through lenses and we managed to finish diverging, converging lens. Today we shall begin with this thing called magnification. Yesterday what we went through is this thing called linear magnification. Still remember what is it equals to? Minus height of object over height of image, right?
Image over height.
It is equals to V upon U or U upon V? V upon U lah. What does the negative sign mean? It means that if it is a negative magnification, it means that it is inverted, correct? Positive magnification means that it is upright. No worries, it didn't mean a lot. It just means quite a bit. especially the diverging lens part. Please go and watch the video.
I watched it.
Yeah. Oh, right. Excellent. Do you like the video?
Yeah.
Okay, good. Okay, now there's another kind of magnification. Is it running? It's running. Okay, there's another kind of magnification called angular magnification. I'm going to explain a little bit more. It's not so intuitive, so you have to listen carefully. Now, when we talk about angular magnification, the counterintuitive part is that you need to have a base. You need to have a comparison. So what's the comparison? It means that if you put your eye here, and then you got your eyelashes.
My
Can?
eyelashes doesn't roll on my eyeball, so
Okay, it's okay. Like this. Okay, this is 25 centimeters. Now, why 25 centimeters? Because 25 centimeters is what we call the near point. Now, in your notes, it is mentioned near point. Go and find that page where it says near point. And read out to me what does it say about near point. Near point is the point, the nearest point where... correct. It's the closest distance that the eye can focus clearly or comfortably without strain. Can? Which page is it? There's no page number. Right. Okay, fine. I mean, find the page with near point. In case they can't find, let me show them where's the page, in case. This one, this page, it looks like this, the human eye. Is it this one or this one? This one.
why is it so laborious being labeled ciliary muscles?
Can? Okay, relax. That's the biology part. Let the biology people worry. Can? All I need you to know is this thing called near point. And what's the distance for the near point for a normal eye? 25 centimeters. Which means that if you can focus closer than 25 centimeters, it means that probably you're short-sighted. Yeah. And if you do this and you can still see, yeah, I think you're imagining things though. If you can focus closer, that means if you actually need to strain a bit, it means that it's not the near point already. It means that you must put here and then you can see. Yeah, if you just put here and then you need to adjust a bit, then it means that it's not comfortable already. Yeah? Like say for example, you put like this, you can see immediately. You put like this, you can see immediately. You put like this, you need to strain a bit, means that it's not near point already. So it's about here lah. Yeah? Shannon, not like this, Can? So that's the near point, about 25 centimeters. So for normal eye, Now, the angle theta is approximately equals to h upon 25. So that's the angle subtended by the object at the near point. That will be used as a reference. Okay? And the angular magnification is defined as the angle subtended by... Subtended means this one, subtended. Yeah? Image at near point or far point, we'll talk about both, over angle subtended by object at near point. Now, what does this mean? What does this mean, right? I mean, seriously, we have gone through this one already, which is that one over there. Okay? So what on earth is this image subtended by image at near point? Now, this is what it means. Can you see that if I place a converging lens, I place the object at the point, the principal focus of the lens. And say the principal focus is only 5 centimeters. See, 5 centimeters versus 25 centimeters. How would the ray diagram look like? Like this, right? Okay? Now, can you see that this is formed at infinity? That means even though it is at 5 centimeters, the image is projected very far away, which you can easily see comfortably. So without the lens, or the object placed at 5 centimeters cannot be seen. But with the lens, it enables you to put the object much closer, and yet you can still see it clearly. You get the idea? It enables you to put the object much closer, and yet be able to see it. So in a way, it is enabling you to magnify the object. the ability to see closer, to see more details with the lens. Okay, so it is not magnification in the way that you learned in Sec 3, Sec 4. It is magnification, not really magnifying in terms of having an image, but it is enabling you to see closer and therefore see more. Okay? Without the lens, you will not be able to see anything at this distance. So, can you see that the angle subtended by the image is height of object? This will be height of object over f for this one. This divided by this. Then some of you say, hey, hang on, this is tangent theta, not theta. Alright? Have you learned in your math that tangent theta is approximately theta? For small theta? Right. So for small theta, right. So yeah, a lot of approximation. Tangent theta equals to sine theta equals to theta for small angles. In radians, So therefore, can you see that for near point, for image form at near point, it will be h upon f divided by h upon 25, which is going to be equals to 25 upon f. And this is in your notes. But more importantly, not just remembering the number, you must understand how it is defined and how from the definition you get this, and then combining the two, you get this. And even more importantly, what does it mean when we say image form at near point and then use a converging lens? How does it actually magnify? Yeah, so it doesn't literally magnify, it just enables you to move the object closer so that you can still see it clearly. Okay? How about image form at near point? This is image form at infinity. Sorry, this is far point now. Not near point, far point, because it's image form at infinity. How about image form at near point then? This is the way you draw the ray diagram. This one. Yeah, so this image is formed at near point, so it's 25 centimeters. This is unknown distance. This is height of object. This is the angle subtended by the image. And therefore, so you remember 1 upon u plus 1 upon v equals to 1 upon f. And what's the value of v? Negative 1 upon f, correct. Negative 25. And then if you multiply by h throughout, I'll explain why we do this, equals to h upon f. Now h upon u isn't at the angle? Right? So h upon u is equals to h upon 25 plus h upon f. Now, if you take that definition, magnification is equals to h upon 25 plus h upon f divided by h upon 25. If you work this out, can you see that this is 1? And this will be a 25 upon f. And this is also in your notes. So when you form the image at near point versus you form the image at infinity, the magnification is different, even with the same lens. Okay? As you can see, it's preferable to form the image at near point because you've got this plus 1 over here. It makes it even bigger. You can put it even closer. Yeah? Just now, it was at the principal focus. Can you see that this now, the object is actually moved closer than the principal focus? Yeah? Now, do you need to know anything from in between near point and far point? Do you need to know? Yes and no. No, if you only focus on IB syllabus. Yes, if you love physics. No. No. Okay, up to you. So, anything between near point and far point, you can derive it using this expression. I mean, you can use this one and then form your V at whatever, minus 30, minus 40, minus 50, up to you. Until minus infinity, then you go back to this expression already. Right? Yaning, are you looking through the board or are you looking at the board?
I don't get it why one of the images is parallel, but then the other one.
Oh, okay. Remember, I mentioned that for your syllabus, you only need to know magnification is defined by angle subtended by image at near point or far point. Your syllabus requires. Not that in this whole world, only these two can happen. Yeah, no. In this world, anything can happen between, the image can be formed at anywhere between near point and far point. Just that for your syllabus, you only need to know these two.
So the first one is?
The first one is formed at far point because it's at infinity. Okay. This one is formed at 25 centimeters, so it's formed at near point. So only those two in your syllabus. Can? Sometimes I tell students that S1, S2, and then let's consider a ray that hits here and here. Then students ask me, hey, so how come the wave only travel in that direction now? No, it's not. I'm just considering one ray, Yeah. Just an example, a case. Understand? So there'll be some questions that we'll go through later on that will bring you through this one. But today I shall focus more on mirrors. Okay. Object over here, where's the image? Okay, where's the image? Yeah, if you don't know this, that's it. Must do your O level again. It's in mirror. It's a mirror. What focal length are you talking about? It's a mirror. Yeah. Okay. So this one, what if I have this one? I got a point here. Where's the image of the point? Same. How about here? Same. So here and here. So here and here, like this. Okay, let us draw some basic fundamental rays, and then you'll see for yourself how to. Then we'll talk about how to combine these rays to form an image. If I have a light ray bouncing off like this, can you see that angle of incidence must be equal to angle of reflection? And that's why it bounces off like this, Okay. Do you agree that there will be a R over here? The radius, that's R, that R over there is the center of, actually it should be C. It's the center of curvature of the lens. So you take a compass and then you draw this. Yeah, right. So this will be the radius. Okay? So what happens is that if I were to direct it towards the center, if I have this ray, where do you think this ray will go after reflecting? Reflecting. Yes, correct. Exactly. Because the angle is correct. Third ray. What if this is F, this is C? What if I were to have a ray that goes like this? F is the principal focus. I'll talk about a little bit more about that later.
Is it a mirror or is it a lens?
It's a mirror that can focus. Yeah. So can you see? I will explain to you why it goes like this. But parallel beam of light is almost like a what lens? What lens? Diverging, not converging. This doesn't look converging, look. Right? It's diverging lens. It looks like a diverging lens. It diverges as though it comes from the principal focus. Now, let me talk about this. Let me clean this up and draw another diagram. And I'm going to show you a derivation that will relate this to this. And see over here. Do you agree that it will reflect such that alpha? Make sense? Okay. Now, can you see that if this were to extrapolate back over here, let's call this a H. Now, can you see that this, and this, okay, let's work out some angle. This one and this one will be alpha. Okay with that? This one and this one also alpha. So this is 2 alpha. Cool? Now let's call this as H. Let's call this distance F, this distance R. Do you agree that tangent alpha is going to be equals to H upon R? And tangent 2 alpha is going to be equals to H upon F. Now if alpha is small, very important, if alpha is small, I take this divided by this. This is going to be alpha. This is going to be 2 alpha. It's going to be half.
Actually, sir, tangent 2 alpha should be equal to F over H1.
Sorry? Tangent 2 alpha is opposite over adjacent.
Oh.
Yeah? Can? So can you see that F is equals to R upon 2? Yeah? It's something you need to remember. That the focal length is half of the radius of curvature. But can you see the assumptions that are loaded in it? First of all, the angle must be small. And can you see that I did not take into account this? Yeah. So not only does it has to be small alpha, that means it's close to the center of the mirror. It only works for a radius of curvature that's big enough. Because if the radius of curvature is big enough, this will be small, naturally.
So what's the definition of the focal point of focal length? And what is
Just like, say, for example, diverging lens, if you got the diverging lens, you will have the light bending away as though it came from here. So like the diverging lens, the focal point, the principal focus of a mirror is the point where a parallel beam of light to the principal axis will diverge, seem to diverge from. So like this one, it will diverge as though it came from here. Yeah, like the lens, like the lens. I haven't addressed the point on how to draw ray diagrams to form an image. So now I'm going to use two rays to find an image. Any two rays. You got an object over here, wham, wham, here, focal point. Where's the image? Where's the image?
It's a whole big thing.
Whole big thing. Which one? This one.
Yeah, actually.
Then how about this?
Then
how about this? Then how about this? Remember, what forms an image? First of all, is it going to be a real or is it going to be a virtual image? Virtual, because it doesn't converge. The reflected rays doesn't converge. So confirm virtual. Virtual means you got to, the line has to be extended backwards, right? Yeah, this is the image. Now you go to the car parks, right? You will sometimes see curved mirrors. The image will always be small, right? It was always small images. So it's always, you don't see the image inverted. It's always upright, diminished, and virtual. And for diverging mirrors, which is convex mirrors, that's what we call them, there's only one kind of image. Like diverging lens. It's always upright, it's always diminished, and it's always virtual. Okay? Not so for concave mirrors that you realize later on. There's a few cases. That we'll go through. Okay? Yeah. Confident now? Any three rays, it should cut at the same point. Which means that if I got a ray directed to the center, it should look like this. It should cut at this point and then reflect backwards. The three rays should cut at the same point. Okay? Cool. Next one. Still the same? Where do you think it will go? This is concave mirror here. Just convex mirror. So where do you think it will go? Just like just now. Just now, the diverging mirror, a parallel beam of light will diverge as though it came from the F. Now it converges when it passes through F. If I got this one and a C, guess where you'll go? Yes, correct. So for this, any two rays will help you find the image. Let's try. C, F. Make a guess. How would the image be? Real or virtual?
Virtual cover.
Yeah, just like your converging lens. Let's try. Okay. Can? Okay, it should connect back to somewhere here. Okay? They should never converge over here. It will diverge, and if you draw backwards, it will connect back here. So it is like the converging lens, magnified, virtual, and upright. Cool? Now make a guess. If you were to have a mirror where I place, this is C, this is F, and I place an object here, how would the image be like? Remember your converging lens, no? If I place an object that's very far away, the image will be real or virtual? Real. And then inverted and then diminished. Correct. Let's check. Let's check. Agree? diminished, inverted, and real.
So isn't F the point of the image under F? Because
No, if it is at infinity, yes, it will go through F. But it is not at infinity.
shouldn't the focal point where F is on the line? On the
Yeah,
focal
this is F. You're saying that this image must form at the focal plane, but why? It is not infinity. If it is at infinity, then when you have a light ray coming through at infinity, like parallel, then yes, it will pass through F. But this is not infinity. Yeah. So as you move further and further back, this image will move further and further back until it hits F. Okay? Cool. So this is how you draw the image for a converging mirror, and what we call a concave mirror. Cool. Okay. Now, up till now, you should be equipped with enough knowledge to do 90% of the questions in the worksheet. So you need to practice. But before you do that, I need to show you 1 upon u plus 1 upon v equals to 1 upon f. Based on what we went through in the mirrors, do you think f is positive or negative for concave mirror? Positive or negative? How many of you see that it's positive? How many of you see that it's negative? How many of you don't know? Does it behave like a converging lens or does it behave like a diverging lens?
on the other side. No, sir, I think it depends on where
This one behaves like a converging lens, right? Because it converges what? Just now, it converges. Yeah, that's why the focal point is the same side image is not a good way to determine. You must look at the characteristics of the ray. I know where you're coming from because the image is formed on the same side as the object hand. Yeah? So it is not a good way to determine. You look at the rays, does it converge? It does. So it behaves like a converging lens, and therefore f is bigger than 0 for concave mirror, smaller than 0 for convex mirror. Okay? You look at what it does to the ray. That's the more important thing, f. Diverge or converge? Diverge, negative. Converge, positive. Okay? And u and v, where do you think is measured from? Where do you think it's measured from? From here? From C? From F? Because it's measured from the center, right? Your u and v measure from the center of the lens. So your u and v measure from here? What? So where is it measured from? Shannon, you okay? You look so like helpless. You look like look at the. It's measured from here. Can measure from the mirror itself. Cool. Can, are you alright? Okay, that's it. Derek, can you stop the recording? Thank you.